Welcome to our next lecture on architectures of AI systems. Now we are going to talk about data drift, which will be the introduction to the model drift, two very important topics, challenges in machine learning operationalization for running machine learning models in production. When we look at the place of those two lectures, data drift and model drift, in our whole projects, we are here in the model drift. And yeah. So let's have a look at our whole picture, most complex picture of data science architecture, machine learning architecture. So as mentioned previously, we have something on the top. On the top we have model experimentation and development stage, or environment, or group of people. So these are the guys who work in the lab. And at the bottom we have a production line. Yeah, so this is what's happening in the production. So we have here model update cycle, model saving architectures, etc. So on top we end up with some machine learning pipeline, which has data prep, modeling stage, which is a source, and then later on pushed to via CI/CD mechanisms to the production, and moving the data, training data through this pipeline results with some repo, which is later then served to customer, deployed and served to the customer. Customer asks the question, and we can monitor the model quality, and in case it decays, trigger the signal to retrain the model using a new data, historical data, to get it updated. So today we are going to focus on that stage. As you can see, we have training and validation stages here. So we need to train the model and then validate this on the data not seen on the training stage. And we are going to talk about how to validate the data itself to compare the training dataset and validation dataset. That is very important because sometimes if we have different dataset characteristics like statistics, mean, etc., between those two dataset, the validation may tell us that the model is good when in fact it's not. So this is the first place where we are going to use data validation methods and tools. And secondly, here, and this is probably the more important, we'll look how to monitor what are the potential challenges, and how to monitor the data incoming as requests from our customers to our model. Yes, and to check whether it complies with the data the model was trained on. So 2 points here for data validation. Once again, not model validation, but the data validation. Okay, so let's continue. Next lecture will be on model validation. Now we are going to talk about the data validation. Very complex area, by the way. So imagine now that we have our prediction service. We have some requests coming from our customers and some answers from our model. At some point of time, the request from our customer may be wrong. What does it mean? For example, we may have a model which predicts the price for a flat in a given city, and it was trained on a data set where we had only 4 floors, maximum floor, 4 floor departments in our city. But times are changing and new apartments appeared with new buildings with 10 floor. So they ask for the flat prediction for the 9th floor, for example. And we didn't have something like that in our Training data. So a model will either generate the error, just a technical error, or provide a wrong answer, yes, because it was not trained for such a situation. There may be also a kind of the typo. A user wants to predict the predicted customer lifetime value of the customer, which is at the age of 54, for example, at a given moment, but by mistake typed 55 and L letter. Okay, so this is a definitely mismatch between the type of the data. So that may be typical error in the data, incoming data to our model. So obviously, we can cope with that problem using different filters, simple data validation scripts which will reject such data, but sometimes it's not that easy to mechanically using some heuristics which are possible to be hard-coded to predict such differences. Moreover, with hundreds of thousands of models in production, where we have thousands of different models here and huge data, big data coming to our models, we need to automate such a data validation because it's close to impossible to control it by hand or by different scripts. Yes? So even it may happen that each such a model is trained for different purpose. So writing a separate code for each of them may be very tedious. So we need there is a need for a kind of the automation of such a data validation process. So before we continue, let's think about what may go wrong with those data, incoming data. Firstly, the distribution of data, inputs and labels may not comply with our training data. So this is the first thing. Next, change in schema. Schema may be different. Next, a relationship between features and labels does not comply. Or data source, for example, maintained by others may be wrong. Yes, so they may change, for example, APIs. All of those points will be covered in details later in my presentation. Or there's another very interesting story, an upstream model, a machine learning model which generates some data for us may be changed. And if you are not aware of this, we won't be ready, our model won't be ready to answer correctly. So these are the the most typical examples of what might go wrong during the data ingestion to our model during, once again, firstly, serving the data, which is the most important problem, but also during that model validation. I already told you that we have this very subtle switch between relation between the testing the model, the training data, and data validation. So let's go into details. So let's talk about now changes in data distribution. These are typically changes in the likelihood of observed values. And now let's have a look. For example, for categorical variables like a gender, in our training data set, we may have that proportion of male and female humans in our data set, but after some time, the incoming requests, when we compute this ratio, look like that. So people ask more for male than for female. Okay, so this is the first thing we should control for. Next, we may also some changes in feature distribution for numerical variables, not only categorical. So that may be, for example, standard deviation shift. If you look carefully at this plot, you will see that both have the same mean, median. Yes, this is the same here, but different standard deviations. So once again, imagine that this is the demand forecasting model. It was trained on the data distributed with for some feature, yes, of the product that way, but later then we can observe that the standard deviation of the statistics of the thousands of requests has for a given feature that shift in standard deviation. So this is another possibility. Obviously, for numerical features, we may have also the mean shift. And if you think a second for a potential situation for that may be, for example, the average price of the product. And this change is because of the inflation. Okay, so we may have trained our model, demand forecasting model, with the mean price for a given stock keeping unit at the level of 10 Polish zloty and 10 US dollars. And after some time, that may be 12, we have inflation nowadays. So this is the typical mean shift in numerical data, and we need to identify such a situation to react, for example, with model retraining or some other action. That may be also changes in the feature distribution and categorical variables, which are already mentioned, and the change in schema. There may be a new value for a gender. So, for example, our customers, when they are asked for the gender, start choosing a non-binary option or some other option like I don't want to say, yes. So it may happen even that problem may rise because of some technical changes in your systems. For example, when your people responsible for the website realize that there is a need for such a change, they could add a new option in this in such a form, and the data with that option will come to us, but we didn't have it in a training data. And for most cases, our model will react with the technical error for a non-binary value. So once again, this is the change in a schema. So for a given feature, we may have dozens, if not hundreds of features in our model. So for a given feature, there will be a new value of the existing categorical feature. So there may be also a missing feature. So this is also typical. In our training data set, we could have, for example, 5 features for one single explanatory variable, a target variable, but in the batch processing data set with requests come to us without one of those features. So we have definitely missing feature, and it may also generate the error. Okay, this is very typically, you need to be careful with that when you use categorical one-hot encoding for categorical variables in your model as a data preparation stage, because as you probably remember, one-hot encoding generates for a given feature generates that number of columns with 0 ones, precisely the same how many we have different values of those categorical values. So if whenever you add a new value, like for example this non-binary option, it will generate 3 values, 3 extra features instead of 2 features as was previously. So we may have some at that time extra features. So by the way, this is another possibility. Reverse, we may have an extra feature in our dataset, but still, as you can see, these are the changes in schema. We may have a missing feature in the request or an extra new feature. That's once again changes in the feature distribution for categorical variables. So let's continue. We may have also changes in label distribution. So previously we were talking about features which are part of the request. Now we are looking at the answer of the model. And imagine that in our training data set, we had the following ratio between high rev and low revenue customers. But after some time when we observe model predictions in the production, it looks like that. So we can observe that there is a growing proportion of high rev customers. So that signals that something is wrong with the reality, and that may be a very important signal to retrain the model. That also may be because of the inflation. Okay, so someone who spent in our store, for example, $1,000 per year, and she or he was in the top percent of our customers, 10 most profitable customers, but due to inflation, okay, it's not that profitable because the prices went up. So we need to also track the distribution of not features but also labels. Next, and this is also very typical, relationship between features and labels may change. So it may happen that in our training data set, we have checked because, one remark, most of the machine learning models, if not all, are based the predictions on correlations, not causal relations, but there are some causal ML techniques which enable you to identify the real causal relations between variables. Once again, if you're interested in that, I recommend you to read something about so-called causal ML, maybe to dive into libraries like PyY or CausalNex. So using these libraries, we could have found that we have some causal correlations between those variables, but later then this causality disappears. So the way is changing. So previously, a few months ago, one variable could really impact another one, but now it doesn't matter for that. So it typically changes because of different aspects in e-commerce, like changing prices, new geopolitical situation, okay, or new competitors on the market, changing habits of the customers. That may also happen in customer categories where there is a strong impact of social media, new influencers, new fashions coming. So that may also generate the model drift. Next potential source of that. We may have a change in the data source. Imagine that in our training the model, the training data set, or during the inference, this is very important, okay, because it may happen also in the inference. We have a request from the user, for example, for the business user for some protection, but having that basic data, we use some enrichments. So we have some extra data sources who help us to enrich the original query. The best example are demographics data taken from external statistical offices. For example, in Poland we have Główny Urząd Statystyczny, which provides the data. Now imagine that we have the customer. The customer provides the postal code, and we have our systems integrated with such a statistical office databases using API, application protocol interface, and request comes as a raw data. Then we enrich this data with external sources and we push such a combo to our model. It may happen that the statistical office changes the format of the data, changes the API, and previously we asked for some data, I got something reasonable, now it's trash. And so we need to have our systems ready for that. Yes, so we need to prepare for the change in the source data. That may be also the change in the library. So imagine that you are using a library for, in our case, in the case of this high revenue example in Python, I used the user agent library, which takes as input some data from the log weblog and results with some very specific characteristics of the computer used by the user. And now with a given version of the user agent library it works perfectly, but after some time developers of this specific library has changed some output, changed the API. I have updated this library just to having just regular housekeeping activities, and the library generates at the moment completely different values than I expected. And obviously it's good if it generates the error. Wow, then I can find it. But it's a bit worse if it generates some value which is acceptable by the model, but generates the wrong prediction. So we need to also take care about that. Change in the library used to prepare data, for example, for requests, okay, because we need to have the same pipeline both for data prep for training as for data prep for inference. And one of the final possibilities is the change in the upstream model. What does it mean? We may have in our architecture a pipeline of models. So let me give you the example. Imagine that you have the recommender system in e-commerce store. And this recommender system recommends some product for a new customer basing on different customer characteristics. And one of those characteristics is the age. Yes, is the age. But you do not have this data specified in the customer data. So you have some customer, but you do not know the age of the customer. So you may do the following. You may have some separate model which takes as input behaviors of the given customer, and being trained on the good quality data previously, generates the output, the age of the customer, or let's say category of age like a kid, teenager, student, adult, senior, yeah, different categories. And that is the input to our model. So I have some data about my customer. I have some data from other model as input, and then I push this combo to my model as a request in order to get some inference. So what might happen? Developers of this model may change the output or the behavior of this model if there are different teams in our company, or if they are external providers of such a model. We need to be informed about this. And if we are not, we need to make our architecture resilient for such errors. So we may have some customer behavior, customer age, and product recommendation. This is the example of the change in the upstream model, the idea of the upstream modeling, and the risk of the changing of such a model for our case. So the customer age modeling team fixes the model, and boom, we have a problem. Okay, so now in my examples, you'll find them on the course folder. I have prepared for you some simple libraries which simulate some data skew. Here you can see some example functions like this simple one, which shifts standard deviation and takes as input the number of the column and the percentage of shift. The same is for shifting the mean, etc., etc. You'll find this in the helper library. And for our case, our use part of so-called TensorFlow extended libraries. So before we continue, just let me shortly describe you what's that. This is the library developed by Google. It's open source. It's not TensorFlow. It's TensorFlow extended. So this is the library for machine learning operations. Extremely large library, very difficult, very professional. It's definitely overkill for you for this project in this course, or I think generally. Yeah, it's very good library, yes, but very difficult. As you can see, here we have some example gen library, here is statistic gen, so we have some training data. We take a sample of this data here. So next we compute the statistics for categorical and numerical variables. Next we validate data. We have the schema generator. We transform the data and then we push this data to the trainer to train the model, tune the model, and then evaluate infrastructure validation and push it to the production. So as you can see, to different endpoints, the endpoints of different types. As you can see, it's whole MLOps process. It stores also a lot of metadata from all those things, so you can track different runs. It's prepared for Airflow, but also for Kubeflow, some other runtimes. And we are going to use, in my code, in the examples you will find, the sub library of that, which can be installed, by the way, as a separate library. It's called TensorFlow Data Validation. Okay. Sometimes if you install it, you may find some problems. I have checked this. It's running perfectly on Ubuntu, but the last versions of that didn't work on my Mac. So if you have problems like that, do not give up. Try to run this on Ubuntu. It should always run, yeah? As you can see in the structure, the screen is taken directly from Google. We have a group of modules to ingest and validate data, train and analyze model, deploy in productions. TensorFlow data validation is here on the left. And it may be used to detect distribution skew between training, testing, validation, and serving data. So as you can see, the skew, which we need to detect and react on. It may be here distribution in training versus data distribution testing data splits. So this is the first thing we should take care about. Next, this skew maybe between data distribution in testing data string and data validation. Okay, and here in the serving. So that's what I previously plot on our schema. So it may also be used to validate continuously arriving data. So imagine that you have, let's stay at the moment in that place because that may be the most interesting for you. So this is the stage where we track the data, potential data skew between the user queries and the data our model was trained. So that may be not only the query as a feature, but also the responses of our model, because we may detect also the skew in the labels, but still we are in the model serving stage, not training and validation, but model serving stage. So we may gather some data from day one, generate statistics with this data, and compare it with the schema and validate. And then we can generate the data from day two, generate statistics, take the data to stats, and validate statistics with the original data, etc., etc. So we can validate continuously arriving data, and at some day, for example, day number 11, we will find, okay, beam, for this feature, whether it's a numerical category, we have some potential skew, and it will trigger the signal to react, for example, to check if something is wrong or maybe to retrain the model. We have many different components. The first component you are going to find is statistic gen component. So this is the sample code. You take the sample data or the whole data you have, but it's better to work in the sample in case you have big data. So it will, for each feature, generate some stats for you, and if you want to visualize that, it's also possible within the notebook if you want. Obviously, for the Python code, you can export this picture if you wish. And it may also generate the schema for you. So generate for a given dataset, whether it's your reference, as it was in the training, or the request, as it works in the production. Yes, it may generate the type of data. Yes, so say, for example, this is float, this is integer, this is string. Yes, so it will also generate this and then compare. So just to compare, you have validator component. So as you can see with this simple statements, you can compare the statistics of input to the reference schema. And in case there is something wrong, it will generate the error. It's very, very subtle. So just I strongly suggest you to follow my codes because they use very different statistics to identify the difference, the skew, whether it's a distribution in categorical variables or some statistics for numerical variables. And you need to specify directly the threshold for this skew to be detected. If you do not specify such a threshold, it won't raise any alert. So in order to get the alert, in order to be alerted, you need to generate this. That was one of the mistakes I made at the very beginning because I changed the data, I didn't get any reaction, yes, and that was the reason. But as I said, it is plainly exemplified in my examples. So that's gonna be our workflow. We initiate the project, contemplate potential problems, evaluation and serving data set, distort numerical features, distort categorical features. Next, we'll detect skew in validation data, compute and visualize statistics, generate baselines, reference schema. I have some protobufs primer for you for the TFDV TensorFlow data validation library. It's below, and then we'll detect data skew for evaluation data set. Next, we'll detect drift in serving data. We generate some series of serving data, perform slice analysis, analyze change over time, detect anomalies between data slices by date and baseline schema, and correct schema for labor error. This is the workflow described precisely in the PDF file with all the instructions provided in the course materials, so you can follow them if you'd like to and go through those examples. Once again, that's very important, but I think it's not obligatory for this course, yes, because it may take some time, but if you would like to walk through this, I think that you'll benefit out of this. So once again, a very important part, but time consuming. If you find time for that, just go ahead. If you don't, just be aware of that. There is some set of problems I described now. They exist, but there's also a solution for that, like TensorFlow data validation, but also some other libraries. So that completes the workflow. Before we complete that presentation, I would like you to tell you something about auxiliary tools, which are protobufs. Protocol buffers, by the way, it's one of the most popular, if not the most popular protocol of sending the data over the internet due to Google engineers. So this is the format of the data sent in machine learning projects. That's as you can see here, protocol buffers are language neutral, platform neutral, extensible mechanism for serializing structured data. So you can read this, or this is the documentation, and it is very useful if you would like to dive into details of the objects generated by TensorFlow data validation, because TensorFlow data validation will communicate its results to you using protobufs. So if you would like to extract this data in order to use it, reuse it somewhere in your pipeline, you need to know this. It's quite simple. It's very similar to XML or like JSON. It's like JSON, except it's smaller and faster and generates native language bindings. It's hyperlinked here, but if you do not have the time to study it carefully, You can follow this introduction to Protobuf, what and why it will take you. As you can see, 15 minutes read time, and I think it's definitely worth to try just to read it once in order to understand how to cope with that. Once again, if you are familiar with JSON, it's JSON-like, so if you can read JSON or dictionaries, you will manage. So that completes our lecture on data drift, and meet you on the next lecture on model drift. Thank you very much.